Okay, welcome everyone. So today what we're going to do is we're going to talk about stoichiometry. So we're just going to run through this first page of the notes. This is probably one of my favorite parts of chem. So predicting products is a highlight, and that's where we got to react the different substances together and try to figure out what are your products going to be when you react these two things, or when this decomposes, what do you form? For example, we did like the hydrogen peroxide. And what did the hydrogen peroxide break up into? Water. Two things, water and? What was that? What were the bubbles that came off? Everybody, what are those? Oxygen gas, nice. And then we tested for the oxygen too, because we know that oxygen feeds a flame. Yay, yeah, perfect. Okay, and so by testing, we blew it out and then checked to see if your flame ends up getting bigger. And sometimes it does, sometimes it doesn't. Depends on how much oxygen was being produced in the reaction too. So what we're going to do now, this is kind of putting a lot of the stuff together that we've been learning from the beginning of the year. So I had spoken to you about the fact that not only would you try to predict products, but let's say that you wanted to make a certain amount of silver. You wanted to make 5 grams of silver and you have silver nitrate. Well, now we know that we can do something like a single displacement reaction and maybe use something like copper. And the copper will do what in the silver nitrate? It'll replace the... Which one, the silver or the nitrate would the copper replace? The silver. Why would it replace the silver and not the nitrate? They're metals. Awesome. So you want the same, what I was calling same type of player, is the one that's going to get replaced. So that part where it ends up replacing, you end up getting the silver that comes out, and you would actually get silver that precipitates out of the solution, and then the copper goes into the solution, and it forms like a bluish type of solution after that. You switch?
No, not that, but like, could you do like any element and like could you use
yeah,
it
no, that's a great question. There is what is called an activity series that you would have seen like in that study guide that you did. It's one of your vocab words, and that basically tells you whether or not it's going to switch. So it depends on where it is in the activity series. They don't always switch places. Yeah, it has to be more active basically than the other metal. Okay, so what we're going to do now is we're going to say, let's say I want to make 5 grams of silver. Well, how many grams of the copper, how many grams of the silver nitrate do I need to start with in order to make 5 grams? So now we're just taking it one more step further, and that's what is basically used in industry and in producing things. So if you want a certain amount of ammonia, you need to react nitrogen and hydrogen in certain amounts. We don't want to be wasteful. We're always thinking about making sure that we're keeping in mind the environment and staying green and things like that. So reacting the proper amounts is also going to be important so that we're not just throwing some of it out, okay, or a whole bunch of it out. So in this unit, we're going to expand our understanding of how chemical reactions can be useful in the world around us. We're going to determine how much of a product could be produced when you know the amount of your reactants. And it doesn't, these two words could be switched. Maybe you know the amount of your reactant and you want to know how much product is going to be made, or the other way around. The question is, what is stoichiometry? Okay? So I start this off by saying, and it's amazing to be able to put so much of what you've already learned together to get a better understanding of the matter around us, which matter is just the study of what? Yeah, that's chemistry. Chemistry is the study of matter. So that's what we're studying, is just matter around us. So with stoichiometry, people will ask you and say, so what are you doing in chemistry right now? Maybe they're also sophomores or freshmen or whatever at a different school. And then you say stoichiometry. They're like, oh, what's that? We haven't done that yet. I think it's like doing math with the I don't know what it is exactly. Here's what I want you to say. We're going to do a quick go around the room. Okay, just a couple people that I'll point to. And you're just going to repeat what stoichiometry is. Okay, it really is just a fancy word for the mathematics of chemistry. But it's figuring out the amount of one substance when you know the amount of another. Everybody repeat it first. What is it? Figuring out the amount of one substance when you know the amount of another. Okay, got it? Okay, so start us off. What is stoichiometry, please?
Figuring out the amount of a substance when you know the amount of the other.
Nice. What is stoichiometry, please?
Me? Oh, when you know
Figuring out
the
yes, when you already
know the other.
Nice, perfect. And let's do second person.
figuring out the amount of a substance when you already know it.
Nice, that's it. Okay, and so what we're going to do is we're going to bring back the mole conversions. If you got mole conversions, this is super easy. If you didn't get mole conversions, what people were saying is, and then I hear this over and over again, I don't know why I didn't get it. This is so easy. Like, I don't even know why I didn't get it the first time. Like, this is really easy. And I think seeing it the second time and waiting a little bit, then it just sinks in. And it's like, oh, that's easy. I'm not sure what I had a problem with. So it says we've been studying chemical quantities and we were doing conversions. The thing is that we were using the same chemical. So when we did, if you look at our switch it thing, before we had just one side of this, okay? Because we only had one substance. And what I had said was it was like taking a subway and this was like Grand Central Station, and so you're going to go to grams, or maybe you're going to go down to liters, or maybe you're going to go to your formula units or your molecules. But the central station is moles, okay? Now what's going to happen is we're going to switch the substance. So instead of saying I have a certain amount of silver nitrate, how many grams of it, how many moles is it? Or how many formula units do I have of that? Instead of just being in one substance, now it's going to be, okay, if I want to make 5 grams of silver, how much copper do I need to start with? How many grams of copper do I need to start with? Okay? Or how much silver nitrate do I need to start with? Or maybe it's liters of a particular gas at STP. Then you can do switching over to find out how much gas maybe you're going to produce of something. And so that's where this double switch it thing is going to come in. And it's kind of like taking a plane now. So here you've got your subway system, but if we wanted to get to London, you're going to take a plane across to London, and then you can use the subway system to get from one place to another in London, for example. Okay? So this here is going to be a jump where you can't just go from grams straight to grams. You actually have to be in moles in order to do this. So what I call this is the mole ratio. Okay, so that's what I'm going to call the mole ratio. So we're going to use this in order to figure this out. I'm going to use an analogy here because you know, let's do this problem and then I'll do my analogy in just a second here. Here's an old problem, okay? This is an old type. So remember, everybody's going to say the circle what you want, write what you got, throw it a bridge, cross units opposite. Here we go, ready? Circle what you want, write what you got, throw in a bridge, and cross your units opposite. Okay, what are you circling here? What are we looking for? Moles, perfect. Moles of calcium carbonate. Now the thing is, we did not have to keep writing that it was calcium carbonate because it's the same stuff. Now it's going to be changing, so I'm going to tell you that now you will have to keep writing the substance. Otherwise, you'll make mistakes and your answers will be off. So I will be looking for that, okay? Circle what you want, write what you've got. We've got the 70 grams. What is calcium, the formula for calcium carbonate? So calcium is Ca charge, 2, carbonate, CO3 charge, -2. So remember the word car is 3 letters, and then it's better to have 2 people in the car. Okay, so cross your units opposite, grams of CaCO3. How do you go from grams to moles? Well, if we look at the switch it thing, what do we need to use in order to go from grams to moles? L chart. Okay, keep in mind that you don't have to do an L chart anymore. You can just add this up, okay? So you can just do it right in your calculator. So it's 1, 1, and 3. Calcium's molar mass from the periodic table is 40.1, carbon's 12, and each oxygen is 16. If you end up adding all of this up, you'll get 100.1 grams per mole. So then where do I write the 100.1? On the top or on the bottom? On the bottom with the grams. Good. So 100.1 grams per mole, and then you're going to divide. And sig figs. That's 3 sig figs. That's 4 sig figs. Go ahead and divide it, and please tell me what you get with 3 sig figs. You want the least number of sig figs. Anyone? 0.699? Perfect. 0.699 is what you should get when you divide. And that's how many moles of calcium carbonate it is. Okay? So that's an old type of problem where we'd be switching from one to another. Now we're going to take it one step further. Stoichiometry is a fancy word for the mathematics of chemistry. We're going to be able to calculate how many grams of a certain compound would be formed if you're starting with a certain amount of grams of a different compound, or how many moles, how many molecules, how many liters. We're going to use bridges to convert from one to another. Okay, we talked about when we did balancing equations, we talked about those coefficients. What are the coefficients? The numbers in front. Do you remember what those coefficients tell us? What do those represent? Starts with an M, you can just say it. Moles. Everybody say it. Moles. Coefficients tell us moles. I like to remember this as like M&Ms. How many of you guys like M&Ms out there? I'm an M&M lover. Yes, not lots of people. Okay. Instead of M and M, it's MLM. Guess what the L is for? Liters. Nice. Liters. Very good. And what do you think the other M is for? Not mass, because the coefficients don't tell us mass. Molecules. Nice. And I'm going to say over here, not mass. Okay? The coefficients don't tell us mass, but what is conserved in a chemical reaction? Think about those laws of conservation. What have you heard? What are the laws of conservation of? Of mass. Nice. So the amount of mass that you have of your reactants has to be the same as your products. What else?
The amount of each element.
Amount of each element. So your number of atoms and the elements, those have to be the same on both sides of the equation. The last one we haven't talked too much about, but there's another law of conservation of something that we haven't really said too much about.
Energy?
Energy. Nice. Energy is also conserved in a chemical reaction. Okay, this can be a multiple choice question. Okay, it can be done in multiple ways. It can be which of the following are conserved in a reaction, or what do the coefficients represent, and I want you to make sure, I wanted to do these both in the same place so that you could see the difference. So if you looked at a balanced equation, like this one right here, remember that that would be a 1 if there's no number there. It's a 1, a 3, and a 2. Well, if these are representing moles, now they don't write it every single time. You can just do it this one time on here. Those are representing moles. If you add up the moles on the left, how many do you get in total? 4. And on the right you have 2. And by anyone's math in this class, we know that 4 and 2 are not equal to each other. Okay? So that means that moles are not conserved. They're not conserved. But we do know that if we had a certain mass of these two, that our mass would actually be equal to the mass of when you put it together. So let's talk a little bit about this before we do this. And it's super easy to work out these problems, but I just want to do one thing, one quick analogy. You know so much about sandwiches, okay, because you've been eating sandwiches ever since you were like 3, okay, or whatever age. So we're going to use a very basic, very, very simple grilled cheese sandwich, okay? As basic as a grilled cheese sandwich can get. And we're going to use this analogy later on too. What would an equation be for a very, very simple, basic grilled cheese sandwich? How much bread? 2 pieces of bread. Very basic would be 1 piece of cheese, equaling out to give us 1 what? 1 sandwich. Pretty simple, okay? Again, you can see that 2 plus 1 does not equal 1. Okay, 2 plus 1 should equal 3. So our moles, in a sense, are not being conserved here. So if I started giving you numbers and I asked you about mole to mole ratios, let me start off with the mass thing. Would you agree that my mass is the same of this side compared to this side?
Yeah.
Yes, because all I've done is I've put these together, so my mass is still the same. Okay, so the mass remains constant between the two. And also, my elements basically are kind of staying, if I called these elements, they're kind of staying the same. I still have 2 pieces of bread and a piece of cheese that are inside of there. Okay, so I'm not making any new type of substance here. So here's where you're going to be really fast. It's with the ratios. If I wanted to make 20 sandwiches, how many pieces of bread should I start with?
40.
Everybody, what? 40.
40.
How quick? You didn't even have to do any type of calculation or anything like that. How many pieces of cheese would that be? 20. Why? Your ratio is 1 to 1 and 2 to 1, right? Okay, let's say that I've had 60 pieces of bread. I'm assuming that I have enough cheese. How many sandwiches could I make with 60 pieces of bread? 30. Okay, what if I had, and then how many pieces of cheese would I use then in that case? 30. Let's say that I had 25 pieces of cheese. Then how many sandwiches could I make? 25. How many pieces of bread would I need? 50. Okay? So you're really fast at this. What we're going to do is we're going to turn it into a math problem, because when it comes to chemicals, it's not so straightforward. You can't see the bread and the cheese, or you can't see these chemicals the way that you see the bread and the cheese. So here's what it's going to end up looking like. For example, on one of the questions, I was asking you, how many sandwiches would you make? So I would circle what I want if I did sandwiches, if I were starting with 60 pieces of bread. And so what you would do is you would say, okay, I'm starting with 60 pieces of bread, throw in a bridge, cross my units opposite, and then I'm going to do my mole ratio. These are representing moles. I'm going to do what I'm calling my mole ratio between these. And what's your ratio of sandwiches to bread from your balanced equation? 1/2. Which means that I am actually, my bread cancels out, and so how many sandwiches would that be? 60 divided by 2 is 30 sandwiches. Okay? So we're going to do the same thing, and we're going to use a balanced equation, and so some of you will be able to do it without actually working the calculation out. Once it gets to be grams to grams, or grams to liters, or liters to moles, or whatever, it gets more confusing. So we're going to do the calculations. Okay? So let's go back up to this first question. So now we've got ratios. We've got a 1-to-3 ratio between these, a 1-to-2 ratio here, a 3-to-2 ratio, so we've got different ratios between them. Okay? Circle what you want. The first thing is, what are we looking for in Q1? Moles. Of what? Ammonia. Which one of these is ammonia? NH3. What is ammonium? Ammonium is different from ammonia. NH4 plus. Good. NH4, a lower 4, and then a plus charge up on top. Okay? So that's ammonium. That's different from ammonia. Then I'm going to start with my 2.50 moles of nitrogen gas, which is not N, but N2. Throw in a bridge. Cross my units opposite. Moles of N2. Okay. So now what I'm going to do is I'm going to just kind of go up and down different rows. Again, I won't be saying names, so I'm going to start in the back left corner. What I first want you to do is, we're at moles here. Can you tell me how you would go, where you would be going if you're in this substance right now? Where's our goal if we're trying to get to moles of another substance? So we're starting here. Where do you think we need to go?
To mole B.
Perfect. Right across the moles of B. And then just say, what is it that we're going to use to get there?
Mole ratio.
The mole ratio. Awesome. That's what we're going to use. The most common question is, how do you know what goes on top and what goes on the bottom? How are you going to know? You don't have to memorize anything. How do you know what goes on the top and what goes on the bottom? I'll give you a tip. What you crossed opposite. Perfect. What you crossed opposite goes on the bottom. The other one that you're trying to get to goes on top. Okay? So, and A and B, sometimes people will say, is this your reactant and this your product? No. I just do it as A is what I'm starting with and B is what I'm ending with. It really doesn't matter what you call A and what you call B. They're exactly the same. So that's the only part that's different. Okay, so now I've got, that's my substance that I crossed opposite. So what I'm trying to get to is NH3. So I'm just going to put NH3 right there. Okay, on the count of 3, I want you to tell me what the ratio is between NH3 and N2. Okay, ready? You think you got it? Yeah. 1, 2, 3.
2 to 1.
2 to 1. Is there anyone that doesn't understand where people are getting 2 and 1? Okay, I heard a 2 to 1 in the very first row here. How'd you get 2 and 1?
2 is from the NH3 in the product.
Good.
And then 1 is from N2.
Nice. If you don't have a balanced equation, you can't do this. It's a ratio. So now, what's the answer then? 5.00. Awesome. Because it's 3 sig figs right there, it's going to be 5.00 moles. Now, you could have figured this out without doing the math, and I'll show you how on this particular one. The question was saying, if I have 2.5 moles of this, then how many moles of this? Well, let's make it easier. If I had 10 of this, then how many of these would I be making? 20. It's a double ratio. It's a 1 to 2. If I made 60 of this, then how many of these did I start with? 30. Okay. Now this is a 3 to 2 ratio, so it's a little bit harder to do a 3 to 2. So a lot of times people just pull out their calculator and just do a 2 to 3 or a 3 to 2 ratio. So it's a lot easier to just do the math. Yes?
Why isn't it 1 sig fig?
Because that's 3, this is just going to be a counted number.
Oh, okay.
So it's just counting as, yeah, it's not something that we necessarily measured. Okay, let's try the next one. So we've got, question is, how many grams of hydrogen gas? So grams of what? H2. Good. Grams of H2. Right, well we've got 6.1 moles of ammonia, which is the NH3. Throw in a bridge, cross my units opposite. Okay. So next person, so now I'm going to have you just take us through. We're starting with moles of NH3 and we're trying to get to grams of a new substance of H2. So on the switch it thing, if we're starting here, where are you going to go first? Up here to grams? Then that's going to be the same substance. So that's still the same substance, and then you're going to be at a dead end. Go across first using a mole ratio, and then what? Go up. And how would you get to grams then using an L chart? Perfect. Awesome. Okay, so let's do that. So next person. Okay. So she was saying that we were first going to do our mole ratio, and we know that we're trying to get to moles of H2. So tell me what the ratio, what your ratio is, something over something right here. 3 over 2. Do you agree?
Yeah.
Yes. Perfect. You're just going to use this equation, and you're going to do the 3 over the 2. Awesome. We're in moles. We don't want to be in moles, but we did switch over. So it was like we took the plane across to the next substance. So next person, what's this last step now? Go from moles to grams. And how do we go from moles to grams? L chart. You don't have to L chart hydrogen. I do like using, just for H2, using the 2.02 instead of using 2.0, because that way we get 3 sig figs, okay? So instead of using 2.0, so if you want to do an L chart, it really just looks like 2 times 1.01, which is 2.02 grams per mole. So 2.02 grams per mole of the H2, and then we're done. Everything cancels out, and we're left with grams of hydrogen, which is what we wanted. So now you're going to multiply and divide. And again, if you use 2.0, it only gives you 2 sig figs. So if you use 2.02, we can stick with our 3 sig figs, which is usually easier to have. Please tell me what you get on this one. Question?
Okay, why didn't you just stop when you had the ratio 3 to 2? Like, why didn't you
They asked us for grams. So if they asked us for moles, we would be done like they did up here. So since they're asking us for grams.
Okay.
4.53.
4.53? No.
18.5.
18.5?
Yeah.
18.35.
Uh-oh.
18.3. Did I write something differently? 18.3?
I got 18.8.
Okay.
3.
So 18.5 grams. Thought it was 18.3 also. Okay. All right, next one. So now we've got, calculate the number of grams of NH3. So again, grams, circle what we want, write what we've got of hydrogen of H2, throw in a bridge, cross our units opposite. Okay, next person. We're at grams of H2, but we're trying to get to grams of the other substance, of NH3. So we're starting here. So what would you do?
Like down.
Down first, perfect, making L chart. Then you're going to go over across by using a mole ratio. And then the last thing you're going to do is go up using an L chart. These L charts are different because that's for substance A and that's for substance B. So keep that in mind, okay? So we're going to end up doing 2. Again, you don't have to actually draw the L chart out. Okay, so let's try this. Hydrogen we already did. So next person, our molar mass of hydrogen is 1, but then, yep, good, 2.02 grams per mole of H2. Don't forget to write H2 because then when you cross opposite, you know you're doing this properly. So I've got moles of H2 there. Okay, next person. So now I'm in moles, so I'm going across to the other moles, and my other moles are NH3. Can you please tell me what your ratio is?
2 to 3.
Do you agree? 2 over 3? Yes, 2 of the NH3s over 3 of the H2s. Keep on going. We have one more step, moles of NH3. And now we're going back up. So if you look at your switch it thing, we started here. We can't go straight across. You can't do that. There's no plane there. It's like you're in Michigan, you're trying to get over to Europe. You actually need to fly somewhere else usually, okay, depending on whether you can get a direct flight. So we need to come down here, then go across, then we can go back up. Okay? So now we're going back to grams of NH3. We need to L chart this. Nitrogen's mass is, anybody know it already?
14.
Let's see, 14, and each hydrogen is 1, so times 3 is 3, so we've got a total of 17.0 grams per mole.
Wait, what should we do?
14 for the N, and 3 H's. Each one's a 1.
One or not?
You can,
It's not going to make a difference.
but it doesn't make, because we're only going to do 3 sig figs anyway, it won't make that much of a difference on this one. So we've got 17 grams per mole. Okay, and then please multiply and divide and tell me what you get with 3 sig figs on this one.
3.03.
3.03?
Wait, yeah.
No?
We got 30.3.
30.3?
We got 30.
30.3. Okay, awesome. 30.3 grams of the NH3. Okay? 2 more. These are going to go a little bit faster now. So now we've got, circle what we want, grams of NH3. Write what we've got, 132 liters of nitrogen, which is N2. Throw in a bridge, cross our units opposite. Okay, next person. If you can take us through and tell us, you're trying to go from liters of one substance to grams of another substance. Okay? So start us off at liters. Where are you going to go first? Up to moles using what?
22.4.
Good. And then where are you going to go? Across to moles here using a mole ratio. And then you're trying to get to grams, so
Go up.
back up using
Wait, the L chart.
the L chart. Awesome. Okay, next person. So start us off. We're in liters. So down here, what number goes down there with the liters?
22.4.
Nice. 22.4 liters per mole. And don't forget to write N2, because then when you cross opposite, you know what's on the bottom already. Okay, next person. I'm in moles of N2 now, so now what can I do? Next person. Yeah. So now we're in moles, so we're going to go from moles of that to moles of NH3. You know what, let me have you see this. Let me just scroll up a little bit here. So what's your ratio of NH3 to N2, please?
2 to 1.
2 over 1. Awesome. 2 over 1. Perfect. And now the last step, we're in moles of NH3. We don't want that. We want grams of NH3. And next person, L chart. We already did the L chart for this, so the number is 17.0. Perfect. And so now we're done. Everything cancels out again, and we're just left with our grams of NH3. And again, we're assuming that this is at STP. Otherwise, you can't use that 22.4, and it's a gas. So now you're going to multiply and divide again, and please tell me what you get.
200.35.
Okay, 200.35. How would you write 200.35 with 3 sig figs? Because I'm seeing 3, 3, and 3. 200 with a decimal point. Good. If you just say 200, that's only 1 sig fig. So 200 with a decimal point, grams of NH3. All right, last one. Circle what you want again. Grams of nitrogen, which is N2. Write what you've got, 6.2 times 10 to the 24th molecules of H2 of hydrogen. Throw in a bridge and cross your units opposite. Molecules of hydrogen. Okay, question?
Okay, for the last one we just did.
Yep.
The 4.
Yep.
Okay, how did you get from like N2 to NH3?
So that's your ratio. That's the only way that you can get across. That's like your plane ride. From one substance to another, you have to do the mole ratio. So if you're looking at your switch it thing, you need to get to moles in order to cross over to the other substance. So this is all substance A, that's all substance B. So that's how you're going to get across. Okay, so in this last one, we've got the next person. We're starting with molecules of A, and we're trying to get to, is it grams of B?
Yeah.
Grams of B. Okay, so just take us through how we're going to get there.
You go to moles.
Perfect, by using
6.02 times 10 to the 24th.
nice,
And then you do the mole ratio.
nice.
And then you do an L.
Awesome. And then L chart. Okay, so start us off on the first one. What goes down on the bottom here with molecules of H2 then?
I don't know. Is it like?
Do you want to look back at such a thing again?
Yeah.
So we're here, and then we're going to go up this way.
Oh, so it's like 6.02.
Nice. Equal to
1 mole.
1 mole. Nice. Okay, so we've got 6.02 times 10 to the 23rd molecules in 1 mole. And again, don't forget to write H2. Okay? If you forget to write that, it's going to mess you up on the next steps. So now I'm going to cross my units opposite. I've got moles of H2 there. Next person in the back. So now I'm in moles of H2. I'm trying to get to moles of N2. Let me scroll back up here for a second. What's my ratio of N2 over H2, please? I didn't hear you. Sorry. What's the ratio of N2 to H2? 1 over 3. Perfect. So I'm going to do 1 over 3 ratio. And the last step, now I'm in moles of N2, and I want to get to grams of N2. So next person, how do you go from moles back to grams? You have to use an L chart. Perfect. And so N, everybody is 14, so N2 would be, everybody? 28. Nice. 28.0. Good. And then we just want to make sure we stop at the 10th place when we do these two. That way we're all getting the same answers too. And then if you multiply and divide, please tell me what you get again. Okay, 96.1. This one has 3 sig figs here, 3 sig figs in the 6.02, but how many in 6.2? Only 2. So how do you make that 2 sig figs? 96. Good. 96 grams of nitrogen gas.
Wait, what was it?
The 2 sig figs. So anytime that you have anything measured, then you're going to use those sig figs.
Yeah,
So
what did he get in the first place?
oh, 96.3?
I
Was it
got
96.1?
I got 93.3.
What if you put like
Yeah, it should be
96?
96 point something. Yeah, you might, maybe there's just one number difference. Okay, so just the 2 sig figs. All right, please go to your Stoich packet real quick here. And oops, that's not it. The answers, just on the first page, if you want to write some of these answers in the margin there. So number 3 is 425, just to make sure you're on the right track when you go to start these. 4 is 83. 5 is 137, 6 is 4.57 E23, and 7 is 136. Okay, that's the end.